The next topic that we want to go through is probability. And again, this is probably something that you've seen in your earlier statistics class, so a lot of this hopefully is going to be review, but we want to make sure that we go through some of these concepts again, because again, they build on things we're doing later in this class and do the business application. So a couple of basic terminology to some things: probability, experiment, outcome, sample space, right? Some of these are probably familiar. When we talk about probabilities, it's the likelihood that an event is going to occur, right? And so we think about probability is important when we have uncertainty and we're not certain what an outcome is going to be. And so a probability is a way to talk about the likelihood of something occurring. We're going to try to be a little bit careful with our language, right? So an experiment is a process that results in an outcome. So in a science class, when we use the term experiment, or when we're talking about experimental data, we mean something very, very particular by that, right? In terms of what's being controlled in a very closed setting. But really, in probability, when we use the term experiment, we're meaning something much more general. We're just talking about some system that unravels what the outcome will be. And many times, that's going to be an uncontrolled environment, right? So I'm thinking about right now, the NBA Finals are going on. There's some uncertainty about who's going to win those. There's an experiment that's being conducted. It's not really a controlled environment, right? But it's a natural process that's going to result in an outcome occurring. That outcome, again, is the observed result of whatever that process is that resolves the uncertainty in the system. The sample space, right? A sample space is just all possible outcomes, right? So at the time that I'm recording this, we've got two teams that are in the NBA Finals: Golden State Warriors and the other team that's in it. Geez, who's the other one that's Toronto Raptors? That's the one who's in it, right? So the sample space, all possible outcomes of who could win the NBA Finals in the year 2019, it's really down to two teams, right? It's not going to be Matt Kutch. It's not going to be a third option. That sample space of possible outcomes are either that the Golden State Warriors win or that the Toronto Raptors win. Those are the only two possible outcomes. But if we listed out all the possible outcomes, that list would be called the sample space, right? So when we're defining some probability, some other terms that we should be aware of, right? So we've got different ways that we can try to assess or measure probability. In a classical definition of probability, we are deducing from some kind of theoretical argument, right? So a lot of the times this is going to be based on a model. And usually it's a model of a distribution of outcomes, but it's very much based on theoretically what the possibility of outcomes were. That's different from looking at a relative frequency approach to estimating probability, which is based on data, right? So another classic example is the Dow Jones Industrial Average, right? So the Dow Jones Industrial Average, you may be familiar with, right? It gets a whole lot of attention. It's an average of a bunch of different stocks in the economy, or not in the economy, but on the stock market. I should be careful with my language, right? So we've never had a 3,000 point drop in the Dow Jones Industrial Average, right? Does that mean it could never happen? That's kind of the difference between classical probability and relative frequency probability. Classical probability says there's some kind of distribution about what all the possible changes in the Dow Jones Industrial Average is, and the likelihood of having a 3,000 point drop is probably way down here in the left-hand tail. It's theoretically possible, but not very likely. That's probably what a classical conclusion would be about the probability of seeing a 3,000 point drop. A relative frequency way to measure probability is said, hey, let's go and let's look at the data. And we could look at all the possible, all of the past data in the Dow Jones Industrial Average. And if instead of doing a theoretical distribution, if instead we looked at an actual distribution of how many of each of the different changes in the Dow Jones Industrial Average is, one thing that we'll know is that, hey, there has never, up to this point, there has never, ever, ever been a 3,000 point drop. If we have never observed an event happening, then the relative frequency probability is 0, right? So classical probability is based on some theoretical possibility of some happening, of an event occurring, whereas a relative measure of probability is based on looking at the data and counting up the frequency with which an event occurred. Subjective probability is something that also often happens where you might ask a panel of experts, hey, what do you think the probability is that we go into a recession? It's not really based on a theoretical model. It's not really based on looking at data, the past historical data, but rather it's based on their judgment and their experience, right? So we see those sometimes. We want to talk through some of these probability rules, and again, some of these are probably familiar to you. When we talk about probabilities in everyday language outside of this class, you may see online that the Golden State Warriors only have a 40% probability of winning the NBA Finals. Oftentimes, outside of this class, we talk about probabilities as percentages. We are not going to do that in this class. We're going to try to stick very carefully to our definition about probabilities and define a probability as being a value between either 0 or 1. Now, I know in your mind, and I do this too, that when I see the probability of 0.45, I think about that as 45%. I'm going to try not to say that, and we're going to try not to think about it that way in this class. We're going to express probabilities as values between 0 and 1. Those two endpoints are important, right? If something has probability of 0, it means it will not happen. If something has probability 1.0, that means it is certain to happen, right? And the values between 0 and 1 are supposed to represent the likelihood of that uncertain event occurring. Okay, when we think about different outcomes, I'm using O for outcomes. This is outcome 1, outcome 2. If I looked at all the different possible outcomes in my sample space, they'd be equal to 1, right? So again, I mentioned this earlier, right? Right now, my sample space of outcomes for the 2019 NBA Finals are either that Golden State wins or that the Toronto Raptors win. That's funny. If I looked at the probability of Golden State winning plus the probability of the Toronto Raptors winning, that's got to be equal to 1, because with certainty, one of those two teams will win, right? That's an important, useful property of probabilities that we're gonna apply to later. Another thing that's useful is we can think about this concept of the complement, right? So if I've got an event A, the complement to that probability, meaning that event not happening, is just 1 minus that probability, right? So again, those are some basic rules about probability that you've probably seen before. We want to add in a few additional terms to this, right? So one of the terms that I want to add is mutually exclusive. Asking a question at the start of this, in your own words, how would you describe what mutually exclusive means? And in fact, can you give an example of two things which could be mutually exclusive? Right? So let's think about two different events, A and B. We say that two events, A and B, are mutually, if they are mutually exclusive, then this rule about probabilities occur. Let's have A represent Golden State winning. Boy, this is my example for the day, isn't it? And B, Toronto Raptors winning, right? So I'm going to assert that those two events, event A and event B, Golden State, Toronto Raptors winning, that they're mutually exclusive. What do I mean by mutually exclusive? I mean that they can't happen at the same time, right? We're either going to have one occur or the other, but they cannot occur at the same time, right? Mutually exclusive means that they cannot occur at the same time. So if we looked at the probability of Golden State winning and we added it to the probability of the Toronto Raptors winning, that's the probability of Golden State or the Toronto Raptors winning, right? If two events, A and B, are not mutually exclusive, then we have this little bit more complicated rule. So here we go. We've got, if we can think about two things that are not mutually exclusive, how about that Golden State, okay, I'm going to switch over and do a different sport, right? So when we think about the upcoming basketball season, I say upcoming, but it's not nearly close enough for me, right? We can think about if we define event A to be that a team from the ACC, from that conference, a team from the ACC wins the whole NCAA tournament. That's event A. How about event B being a team from North Carolina wins the NCAA tournament. And in case you don't follow basketball as much as what I do, I don't follow it a lot, but I like basketball a lot, right? There's a whole lot of teams in North Carolina that are part of the ACC, right? The ACC is going to include NC State, where I went to grad school, and Duke and UNC, where I did some of my grad work, and I can say that I hate Duke and I like UNC. And there's a number of different teams that are in the ACC that are also part of that are located in North Carolina. There's also some teams that are part of the ACC that are not located in North Carolina. For example, University of Virginia, right? That's a big one that is not, it's part of the ACC but not part of NC. So we've got mutually exclusive, right? We're considering these two events, and I'm going to assert that they're not mutually exclusive. Mutually exclusive is when they can't happen at the same time. These two events, they could happen at the same time, right? It's possible that you could have a team from North Carolina win the NCAA, and it's possible that you could also have an ACC team win the NCAA tournament, right? It's possible that both of those events, events could happen at the same time. For example, if Duke wins. So here we go. To calculate the probability of non-mutually exclusive events, notice it's got a lot of parallel to what we had before, right? Where we've got the probability of an event occurring, of A occurring, plus the probability of B occurring. But now, because there is some overlap, because Duke, UNC, NC State are where the overlap between these two events occur, we need to subtract out the probability that both of these things occur, right? So the probability that we have both a team from the ACC and the probability that, and a team from North Carolina, that we need to subtract out that probability to find the probability of A or B with non-mutually exclusive events. In the background of all of this is this concept of unions versus intersections. So whenever I think about unions and intersections, I often think about Venn diagrams, right? Do you remember what Venn diagrams are? If I draw these two, the ones on the left, the ones on the right, is it clear which one is the mutually exclusive set and which one is not the mutually exclusive set? If we're talking about a union, right? A union is when we've got everything, right? So if I've got on the left mutually two events that are not mutually exclusive, that union is going to include this part that overlaps. If I have two events that are not mutually exclusive, or that are mutually exclusive, the union of those two events are going to be equal to the area, and there's no overlap, right? My union is when I use my OR language, right? If I'm doing the probability of A or B, I'm looking at the probability of the union of A with B, right? And if they're mutually exclusive, it's just the individual probabilities. If they are not mutually exclusive, then I've got a little bit of the overlap, right? We can also talk about the intersection. So if we talk about the intersection, if I have two mutually exclusive events, there is no intersection. If I have two events that are not mutually exclusive, then I've got this little bit of overlap that I don't want to double count. That's the piece where we're talking about the intersection. We're making this, when I have two events that are not mutually exclusive, I've got this little piece that I need to adjust for because of the overlap between the two. Other probabilities that that you may be familiar with, but maybe don't have this language for, right? The joint probability, the conditional probability, and the marginal probability. And so the way that I want to motivate this, I'm going to write down some probabilities with some notations, and then I'm going to ask you for what your subjective belief is about these probabilities. Let's do P for probability. What do you think the probability is of getting an A in this business analytics class? So again, give me a number that you think represents the probability of getting an A in business analytics. And what I'm going to do is I'm going to go and look at some data to see, based on the relative frequency of observations, what the estimated probability of that thing would be, right? That's one probability that I want. We can also think about the gender composition of business analytics. Let's think about what's the probability that if I randomly chose a student that has taken business analytics, what's the probability that that student would identify as a female in this business analytics class? I'm doing B001, but it's B2001, right? What's the probability that I have a student who is a female in business analytics? So basically, right, what's the complement to students who identify as females? Right, that's my male students. So those two probabilities have to add up to 100%. But you could think about, yep, on average, how many females are there in a business analytics class? That's what this value would represent, right? So we've got these two different probabilities, and now I want to ask an additional question. What is the probability that we randomly pull out a student and that student got an A and was a female? What's that probability? Notice, right, we've got the probability of getting an A, the probability of getting a B, the probability of getting a C or a D, right? And I've got the probability of, I'm going to think of the binary gender here, the males and females in that whole thing, right? So I've got a lot of different events here, but I'm looking specifically at this intersection of A and F. So grade of A and F for female. That's one thing. Now I want to do one other, I got to make some room for this. I want to do one other quick little calculation or ask you for what your assessment of a probability is. So this last probability that I want to hear from you about is the probability, I'm going to write it like this. So this line right here means that we're dealing with a conditional probability. So it means given the thing that we have after the line, given that information, what's the probability of this event? So here we go. This is the way that we'd interpret it. If we looked at all of the females who had taken business analytics, what's the probability that randomly we would pull out a student and that student will have received an A in business analytics? Right? That makes sense? Given everybody who was a female in business analytics, all of those females, what's the probability that I would randomly draw out a student and that person would have an A? That's fourth probability that I want you to do, right? So we've got some names for these things, right? So what we've got is these probability of getting an A or the probability of getting a female. We refer to those as marginal probabilities. It's the probability of an event irrespective of any other events. Joint probability, well, we've already got an appeal to that, right? So this guy right down here is the joint probability where we're looking at the intersection of two events. But most usefully is this idea of a conditional probability. It's giving us the probability of an event conditional on some other piece of information. Conditional probabilities drive a lot of what we're going to do in the future with these different kinds of probabilities. We've got a couple of rules about conditional probabilities that connect some of these concepts. So here we go. I've got this notation here. This is looking at the probability of an event A conditional on the event B happening. It's equal to, I calculate this thing as, in my numerator, the intersection, right? So I've got the probability of A and B divided by the probability of B. The way that I calculate the conditional probability, I look at the joint probability and divide it by the marginal probability. There's this nice little relationship, but notice we've got a little bit of algebra here, right? So I could take my different pieces to this and I could manipulate this algebraically, and what I'm going to find is that the joint probability of something, the joint probability of two events, is equal to the conditional probability of A given B times the marginal probability of B, or equivalently it's equal to, notice that these are flipped of each other, the probability of B given A times the probability of A. So real quick, notice that again these conditional probabilities are flipped of each other. They're not necessarily the same value. Go back for a second, and a follow-up question would be, A little bit ago I asked you for what your assessment was on this probability of getting an A conditional on female. How about this one, right? Can you put into words what this conditional probability represents? Can you come up with a value that you think it might be? And lastly, what's really important is this term independence, right? We can think about two variables either being, or two events being dependent or independent. It's based on this. This is pretty critical, right? So if we look at the probability, the marginal probability of an event, if it's equal to the conditional probability of that event conditional on something else, then we would say that A and B are independent, right? For example, what if we looked at the probability of getting an A conditional on you being above 6 feet tall? What value do you think that has, right? If I had to do a subjective estimate of this thing, I think that this would probably be somewhere around 0.25. If the overall probability of getting an A was also 0.25, not 0.6, but 0.25, then what's it saying? Overall, your chances of getting an A are 0.25. Your probability is 0.25. If we looked restricted and just looked at the people who were over 6 feet tall, their probability was also 0.25 of getting an A. It seems like whether or not you're over 6 feet tall or not over 6 feet tall, that really looks like it has no impact on your probability of getting an A. We would conclude statistically, right, that your probability, you getting an A and how tall you are, being over 6 foot tall, those two things are independent of each other. They do not depend on each other, right? So the idea of connecting a conditional probability with a marginal probability and whether or not those two things are equal to each other, that's really powerful. And we're going to come back to that idea a couple of times throughout this class. What else do we want to talk about? We can talk about random variables. Random variables, right? When we think about, we can think about a lot of things, but it's any time that we can come up with a numerical description of an outcome from an experiment. It's a very, 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 very general language to describe what random variables are. But in general, right, we've talked a little bit about different variables that we can use to measure things. If we don't know everything and there's some uncertainty, then it could be the result of a random process. If you recall, we did that example last time about different sales within a month of different products, right? Those sales are a random variable, right? It's an outcome, and there's some uncertainty with it, right? There is an experiment that's going to reveal how many sales there were in a month, but we don't know exactly how many sales there are going to be beforehand. So even sales, we can consider that a random variable, right? In general, random variables fall into two categories. They're either discrete or continuous. Discrete random variables are when the outcome of the experiment is going to fall into a category, whereas a continuous random variable, it's along some kind of spectrum, right? So again, if we think about, if we randomly selected someone in the US and we identified which state they lived in, there's a certain number of buckets that that value of states could take, right? There's 50 different possible outcomes. But there's no in between Ohio and Michigan, right? Whereas if we tried to measure what the temperature was outside, right, that's a random variable, right? There's a whole spectrum, there's a whole continuous set of values that value of temperature could take. Probability distributions. A probability distribution is when we look along, when we characterize all the different possible outcomes that we could have. We can think about probability distribution, and again, you've probably seen a lot of probability distributions, most commonly like the normal probability distribution. It's got some nice properties that you're probably familiar with. We can think about probability distributions in two different ways. They can either be theoretical, meaning they're based on some underlying mathematics and logic, or they can be empirical. When you see the word empirical, you should be thinking about the word data, right? So if we just counted up a bunch of the data that we had and estimated the frequency of different events, in essence, what we're doing is we're estimating an empirical probability distribution. Again, a lot of this is just some terminology that we're going to use. Our probability functions, and again, a probability function is going to be a function that simply just describes the probability of outcomes. So sometimes these things are really, really complicated. Like, again, I'm going to jump straight to the normal distribution. That's a great normal distribution right there, because it's probably one that you're familiar with. That normal distribution that you've drawn all those times in your earlier statistics class, did you know there was an equation that would actually describe that line, that would describe an outcome that starts very, very low, then goes up towards a peak, and then tapers back off? There is an equation. It's a very, very complicated looking equation, way beyond what we needed in this class, but fundamentally, right, it's a function. It tells us for a given value of the thing we're measuring horizontally, what's the value of the probability, and that's what probability functions do. They tell us for a given event, what's the probability of that event occurring. These probability functions, sometimes they're referred to as probability density functions, or PDFs. The textbook here calls it a probability mass function, but I've seen PDF a whole lot more. They've got some nice properties that are going to be familiar to us. Number one, the value of the function is going to be between 0 and 1. Why? Because it's telling us a probability, and probabilities are bounded between 0 and 1. Right? We've got, I'm going to skip over that because that's just a bunch of unnecessary notation for probably this level. A cumulative, well, yeah, this is an important distinction, right? So what a probability density function or probability mass function does is it tells us for a given event, let's call it X, the function will tell us the probability of that event. What a cumulative distribution does is it tells us the total probability up to that event. And that might not make a whole lot of sense now, but in a little bit we're going to jump over to Excel, and this difference between a marginal probability, which is what probability functions do, and a cumulative probability, we'll illustrate that in Excel, and hopefully it'll make a little bit more sense when we get to that point. Discrete random variables. So when we talk about discrete random variables, we're talking about different discrete events. So again, we're thinking about different categories where there's no in between. It's either in this group or the other group, right? We've got mutually exclusive categories. That's what discrete random variables have to do. So we've got this motivator on this. You've all done some kind of charity raffle or something like that, where let's assume that they have 1,000 tickets and they're going to draw out one winner, and that each of those tickets are sold for $50 each, and there's a total prize of $25,000, right? So this is a little bit of a fancy raffle. We can think about, what are the outcomes? For you buying a ticket, what are the two possible outcomes? Number one, you win. Number two, you lose, right? Those are the two possible values, right? So I can define my X to be a random variable, because there's some randomness as to whether or not you win or lose, that simply defines whether you win or lose. And I can even go a step further and talk about X as measuring the change in your financial position, right? So that first line where X is equal to -50, that corresponds to you losing. You buy a raffle ticket, which costs $50, but you lose. The other outcome is when you buy a raffle ticket and you win, right? When you win, you still had to spend the $50 to buy the raffle ticket, but now when you win the $25,000, so $25,000 minus the $50 you spend, that's you're in essence your net change in your financial position. So we've got this, there's some uncertainty about whether you're going to win or lose, and we've got these two different outcomes from winning and losing, either being $50 behind or being up $24,950. I want to ask a question. What is the average of your outcomes? All right, so we know how to calculate the average, right? We just add them up, divide by the number, right? So add them up, divide by the number of outcomes that we have. We have two outcomes there. the average outcome is something, but think about how ridiculous that value is. It doesn't tell you very much, right? What is a more useful metric is this thing that we call the expected value. The expected value of a discrete random variable is equal to, we add up all the different outcomes, so that's where the sum of x is, but we weight those outcomes, we scale those outcomes by the probability of them occurring, right? So the long way that I could write out estimating the expected value of the outcomes, not the average, but the expected value of the outcomes, right? I've got two different outcomes. One of my outcomes is -50, and the other outcome is 24950. But I want to weight those outcomes, I want to multiply those outcomes, I want to scale those outcomes by the probability of them occurring, right? Yeah, right? You have one of the outcomes is losing $50. That's going to happen a lot. If there's 1,000 tickets and you only buy one, my goodness, right? What are the odds? What's the probability that you do not win? Oh boy, the probability that you don't win is 999 out of 1,000. That's where the value of 0.999 comes from, 0.999. Whereas the outcome of gaining $24,950, that outcome happens, but ooh, goodness, it barely happens at all, right? It does not happen that frequently. It's only a 1 out of 1,000. Notice these two add up to the total 1,000 possibilities times 0.001. So real quick, pause and make sure that you can carry out this math. Hopefully you've carried out that math, and if you've done it correctly, you should see that the value is -$25, right? So that's different than the average of the outcomes. It's the average probability weighted outcome, right? So another way to think about this is if we drew out this spectrum, we've got, if we tried to draw out this distribution at -50, way down here, -50, right? We've got a huge amount of the probability, because that's where most of the probability is going to occur, right? Is back here with losing 50. And then at the other big end, very, very, very small probability that you get $24,950, right? The average of those two, right? When you calculated the average of those two outcomes earlier, right, you're basically just taking the middle of those two values, right? But what that fails to take into account is that this outcome of -50 happens so much more frequently, right? And so we put a whole lot more weight, because it has a higher probability, we weight it by the probability, and it gets a whole lot more weight in the calculation of the probability weighted average, right? So another way to think about this, right, is the way that I like thinking about expected value is if you had a distribution of outcomes and their probabilities, where would you have to put your finger in order to balance out this distribution, right? If you tried to put your finger right in the middle, you're clearly going to be way too heavy on this left-hand side and it's going to tip over, right? In order for you to balance this thing out, you're going to have to put your finger somewhere around here, right? Not quite all the way down here at -50, but a little bit to the right, because there is this low probability but very high value way, way, way out on the other end of that fulcrum that's gonna balance things out. The expected value is in essence where the balancing point is on a distribution, right? It's the probability weighted average, or formally, it's the sum of all the values of outcomes multiplied by the probability of those outcomes, right? There's an alternative way that we can think about expected value is, what if we really had 1,000 tickets? What if we really had 1,000 people show up and participate in this raffle? Of those 1,000 people, one of those people is going to experience the net change of 24,950, and 999 people are going to experience a $50 loss. What's the total amount of gains and the total amount of losses, right? So we've got one person who gains 24,950, and we've got, oh boy, I got to do that calculation too. So we've got 999 people who all lose $50. They lose 49,950. They lose, the total group loses 49,950. So what are the total change? The total change in the gains and the losses. So if I took the total losses, and this was negative, right? And I got a 950 in there, and I take out the total gains, right? Then we'd have, this is going to be negative $25,000 would be the total gains and losses. But I had 1,000 people, right? So if I divide all of those gains and losses over those 1,000 people, on average, what would we expect to happen? On average, negative 25,000 in losses divided over 1,000 people. Yep, that's the same negative 25 that we found before, right? So what the expected value is if we had a big group of people who all had the probabilities of these outcomes and had those outcomes, what the average outcome is going to be. It's different from calculating simply the average of the outcomes, though, right? Rather, it would be the average outcome for a group of people who were sampled from this distribution. It's the probability weighted average. That's what the expected value is. And it's a term that we're going to use a couple of different ways and are going to be useful. There are a few more distributions that we want to consider. One of them, the Bernoulli, and related to the binomial distribution. This is a form of a discrete random variable. It's when we have a number of events and there's a probability of success or failure. So this is useful when we've got two outcomes, right? The classic example is thinking about flipping a coin, and that coin is going to come up either heads or tails, right? So this is a way to count up the number of times that we have a certain outcome when we have a dichotomous or a binary set of outcomes, right? And so there's this really, really complicated formula that you would never need to do. Instead, what we can do is we can switch over to Excel and see how could we estimate the binomial value of something in Excel. In order to find binomial probabilities, we need a couple of different pieces of information. We need to know what the probability of success is. We need to know, the probability number of success. Did it again. We need to know the number of successes. We usually just use S for that, right? And then we also need to know the total number of trials. We usually use N for that one. For successes, we're saying how many times do we observe the thing that we care about, and we usually call those things S's, right? The probability of success as the probability on an individual outcome of having that, right? Again, if we think about flipping a coin in evenly sided coins, let's define success to be having heads, right? The probability of getting heads on a fair coin is 0.5, right? There's an equal chance of heads or tails. What if we flipped a coin 10 times? 10 would be the number of trials. What do you think the odds are if we flipped a coin 10 times of observing 5 of those times we had heads, right? So again, success, we got to define what the success is in terms of event, and it needs to be binary, so it's either heads or tails. The probability of that success occurring, counting up the number of successes out of a given set of trials, right? So those are the three pieces of information. And now what's the probability of getting 5 heads out of 10 flips? That's in essence what this is. Let's go ahead and do equals and start typing out a formula. So if you just start typing BI, it brings up a number of different things. We've got binomial, a couple of different things that are related to binomial, right? Notice the description that it's got here. It returns the individual term binomial distribution probability. The binomial dot inverse returns the smallest values for which the cumulative binomial distribution. Let's go ahead and do the binomial distribution. Okay, so again, doing the binomial distribution, we bring that up, binomial.dist, and then I go and I highlighted that one, and I'm going to hit Tab, and it's going to bring up, again, with the way that Excel is structured, it's got a number of different parameters that it's looking for. Number of S, that's the number of successes. What was the number of successes? That's the one that we had in B2. What's the next argument? The number of trials, the number, total number that you're looking out of, right? So we did 10 flips of the coin. That's what we had in B3, comma, and now what's the probability of an individual success, right? So the probability on an individual trial of having success of heads was 0.5. That's what we had in B1, comma. Notice there is one more parameter that we need. So this is the difference between that probability, cumulative probability, and the marginal probability. Let's go ahead and for this one, because we're asking for exactly the number of 5, that's going to be a marginal. If we're doing something with an inequality like 5 or less or 6 or more, then we'd need to think about the cumulative. But if we want exactly 5 outcomes, let's go ahead and do comma. False is the way that it does the probability mass function. Oops, do I need to type out that whole thing? I can just hit the enter. Nope, I do need to, sorry about that. I do need to type out the whole word false. The probability of flipping a coin 10 times and getting exactly 5 heads is 0.24. What's the probability of getting 6 heads, right? This is the reason why I built this as a formula, so that I can change this. Hey, the probability of getting 6 heads is a little bit less, right? We'd expect, on average, that the most common outcome would be we get 5 heads. What about, could we get 6 heads? Sure. Could we get 7 heads in a row? Could we get 8 heads in a row? Not in a row, but 8 out of 10, I should be saying. I've got to be a little bit more careful. Is it possible that you could get all 10 coin flips as heads? Yeah, right? This is the probability of getting 10 out of 10 coin flips as head. It's possible. It's not very likely. Think about how many decimal places there are, right? If we had 10,000 students, right, about one of them would end up randomly just getting 10 heads in a row, right? Great. Can we do one other thing with this formula, though, right? So I want to back it up, and instead, let's go number of heads, and let's do the probability of that number of heads out of 10. And so, yep, I've got 0, and let's go ahead and add 1 to this. And then if I take that, right, I can copy this down my list, and let's reformulate the exact same thing that we did, right? So it's got the binomial distribution, the number of x's. Let's go ahead and select A8, because I'm going to copy this formula down in a second. Let's keep the number of trials held fixed. So again, I'm using my values up above, and I'm locking them into an absolute position. The probability, let's lock that one in as well. And let's go ahead and do false, because we want the marginal probabilities for all of these as well, right? If I copy, now I can just copy that formula down the whole list, and it gives me these values that we found earlier. Notice, what's the probability of having no heads in a flip of 10? It's symmetric. It's equal to the same probability of getting 10 of these, right? Real quick, could we do a little picture of what this thing would look like? Right under my insert, if I go under my recommended charts, I bet that it's going to recommend a nice little graph like there. I believe under the all charts, we can also do a I don't want to do the histogram. Let's do back to the all charts. That's a nice little one. This is a probability density function for a discrete random variable. It's counting up the probability of different amounts of heads out of 10 flips. And not surprisingly, it's symmetric, right? And it has its highest value on the expected values, right? If we did this 10,000 times, on average, we're going to, on average, have 5 heads out of 10 if we do this repeatedly. What's nice about the way that we just did this, we constructed this whole thing, is now we could change some of these parameters at the top. Like, what if instead you had a skewed coin so that it came up heads 55% of the time, right? Right then, we don't have a symmetric distribution anymore. It shifted a little bit to the right. Think about how that might influence the expected value as well, right? What if we go even more dramatically? What if there's a 0.75 chance? Then clearly, right, if it's 0.75 probability of heads, then we'd expect out of 10 to have many more heads. then the probability of having 0 heads would be much, 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 much lower, right? So again, we're just implementing how to do a binomial probability. This is useful when you've got a binary outcome, right? It's either heads or tails, and we're counting up the number of times that it happens out of a certain number of trials. There are many different examples, but can you come up with another example of where, specifically in business, it might be useful to think about a binary outcome, either yes or no, and counting up the number of those things that happen? Let's see if you can come up with a good example. I'm going to jump ahead to a uniform distribution. A uniform distribution, as its name implies, right, that the probabilities of outcomes are uniformly distributed, right? So when you think about if you've got a six-sided die, if you toss that thing, what's the probability that a 2 lands facing up, right? It's an equal probability as the probability of a 5 landing up, right? So uniform distribution is just when you have equal outcomes of things, right? Another way that this can be useful is you think about, stop right now and look at what your clock says. Like, what is the digit on the seconds of your clock, the very last digit, right? So mine is an 8 when I just pulled it up, right? The digits run between 0 and 9, and each of those outcomes are equally likely, right? There's no reason why to expect that one of those digits would be more represented than others, right? So I mentioned this mostly in passing, but if you're thinking about doing some accounting or some fraud, if that's something that you want to investigate, right? There's some, and again, I'm not an accounting person, I'm not an auditor, but there is a way to try to use the what should be a uniform distribution of different values. Sometimes you can dig into people's financial information, and if it seems that there's a specific pattern that's showing up that isn't uniformly distributed when it should be uniformly distributed, sometimes that's been used in different cases to try to identify different fraudulent behavior. The last kind of distribution that we're going to talk about is the normal distribution, and again, you probably have a fair amount of familiarity with this thing. There are 4 main properties of the normal distribution. Number 1, a distribution that is a normal distribution is symmetric. Question, in your own words, what does it mean for a distribution to be symmetric? Another of the characteristics of a normal distribution, the mean, the median, and the mode are all equal. So again, right, this classic example about a normal distribution like that, the mean or the expected value right in the middle. The median, meaning where's 50% of my data, also right in the middle. And the mode, the most commonly occurring outcome, also right there in the middle. So mean, median, mode are all equal. That's a nice thing. 3 is probably the one that we get the least attention on in a class like this, right? Is that it's unbounded, right? So the value of what we're measuring could take on any value. Stop and think for a second. Could temperature follow a normal distribution in an area? Can temperature take on any value? Right, so we've got the value of x is unbounded, but sometimes there are times when there actually are some natural bounds to these things, but we're still going to go ahead and treat it as if it were normal. And most importantly, a normal distribution is going to follow the empirical rule. We've talked about the empirical rule in an earlier topic, but it basically means, right, that when we look 1 standard deviation out from the mean, 1 standard deviation out from the mean, from either side of the mean, that's going to capture 68.2%. If we go 2 standard deviations out from the mean, that's going to be capturing 95%. And 3 standard deviations, oh my goodness, 99.4. And so again, you probably have a fair amount of familiarity with this normal distribution, but we wanted to make sure that we talked about these 4 main properties and that you could articulate what they represent in words. We're going to use normal distributions moving forward in a very, very specific way.